All right, let's dive into this topic of PFAS today.
Okay.
And to be honest, it's not exactly a walk in the park, is it?
No, not really.
These forever chemicals, they're everywhere. And figuring out how to get rid of them has scientists, really scratching their heads.
It's true, and we've relied on them for so long, They're in everything, from nonstick pans to even firefighting foam.
Oh, I know.
But that strength, that's also their downfall. They just won't break down in the environment.
Exactly. And that's what makes this deep dive so interesting, right? Because we're going to be looking at some really groundbreaking research that could totally change how we deal with PFAS.
Really interesting stuff.
Yeah. It's like, we've been trying to trap these slippery chemicals for ages, but what if we could actually just, destroy them completely?
And that's what this research is suggesting, that it might be possible.
I know you've been looking into it, all the research, and it sounds like scientists might have figured out a way to turn these forever chemicals into, well, not so forever chemicals.
Yeah, it's pretty incredible, to be honest.
So far, what have we been doing? I mean, it's things like activated carbon filters, right?
Yeah, it is. And they're really good at trapping the PFAS, but they don't actually get rid of them, do that. It's like we're just kind of shoving them in a drawer and hoping they just disappear.
Yeah, like out of sight, out of mind.
Exactly.
But we know they're still there, just kind of concentrated in that filter somewhere.
Yeah.
So what makes this research different? Give us the headline.
This new method, it actually breaks those PFAS molecules apart, completely gone, really gone.
Okay, now that's what I'm talking about. That's what I call progress.
It's exciting.
Yeah. Before we get too excited, how does it actually work? What's the secret ingredient? What's the magic formula?
You'd be surprised to hear there's no magic involved. It's actually really clever chemistry using some pretty simple and readily available things. They use things like sodium hydroxide.
Wait, sodium hydroxide, hold on. The stuff that people use to unclog their drains, that can dismantle these super persistent chemicals.
It's true.
Get out of here.
And here's the best part. This process, it works at a really low temperature. This isn't about, incinerating PFAS at thousands of degrees. It's about breaking them down at a much more, shall we say, manageable level.
So we don't need some supervillain laboratory with bubbling green goo and, all that crazy stuff.
Not this time. This is elegant. This is elegant chemistry, not brute force. What they've done is they've figured out a way to target a very specific part of that PFAS molecule, almost like, it has an Achilles heel.
Okay, now you've got me. I'm hooked.
It's really quite incredible.
Walk me through it. How do they exploit this weak spot?
Okay, so imagine the PFAS molecule like this really tough knot, nearly impossible to untie, right?
Okay.
Now, this new method, it targets a very specific bond in that knot, and when they break it, the whole thing just unravels.
Wow.
Yeah, it's called defluorination. It's removing the fluorine atoms that make PFAS so durable.
So they just kind of snip the threads that hold the whole thing together?
Exactly. It's like disarming a ticking time bomb.
I like it.
And without those fluorine atoms, PFAS, it loses its forever chemical superpowers, and they break down into much less harmful substances.
This is incredible. But, science can be full of surprises, right? What was the most unexpected thing about this research? What was the thing that really kind of caught you off guard?
Well, we always thought that PFAS broke down in a really predictable way. If you imagine cutting a chain just into smaller and smaller links.
Okay.
But this research showed that it's actually way more complex than that. They found these unexpected byproducts, things like formate and carbonate ions, which are much, much less of a concern.
So it's not just about making smaller PFAS. It's about transforming them into something completely different.
Exactly. And that's a game changer because it challenges everything we thought we knew, and it opens up all these amazing new avenues for research. We might find even more efficient ways to do this, to break down these chemicals in the future.
That's really exciting.
It's very cool.
This is all super interesting, but how much of a difference can this really make for the whole PFAS problem?
Yeah.
I mean, we're talking about a massive family of these chemicals here.
You're right. It's not like a magic bullet for every single PFAS out there.
Right.
But here's the thing, and this is what's really interesting, is that the researchers didn't just stop at testing it on one type of PFAS.
Right.
They actually found that it worked on others too, like even Gen X.
Wait, hold on. Gen X, that's the one they started using to replace PFOA, right? It's like we're trading one problem for another.
Yeah, and the scary thing is for a while we didn't even know how to really break Gen X down.
Right.
But this new method, it seems to work just as well on Gen X as it does on PFOA, which is,
Okay, so now we're talking. Now we're not just talking about tackling one PFAS. We're talking about like a whole group of them, potentially.
Exactly. And they even saw some promising results with some of the more complicated PFAS structures, like those branched perfluoroalkyl ether carboxylic acid. So
Oh, wow.
it really does suggest that this method could have some really broad applications.
Yeah, so this isn't just like a niche solution. This could be something that's, a big step towards a much bigger cleanup effort.
Yeah, I think so.
But let's talk real world for a second.
Yeah. Sure.
How do we actually scale this up?
Right.
Like if I'm living in a community that's got PFAS in the water, what does this research actually mean for me?
Well, that's the million-dollar question, isn't it? Like with any new technology, there are always hurdles to overcome. Right now, it's still early days. We need to figure out how to make it work on a much larger scale. In the real world, it's a lot messier than a lab.
Right.
And
But it's not as simple as just dumping a bunch of sodium hydroxide into the water supply and calling it a day.
you wish it were that easy.
I know, right?
No, we've got to optimize it. We've got to make sure it's actually efficient, make sure it's cost effective on a big scale.
Right.
And of course, we have to make sure that it doesn't have any unintended consequences for the environment in the process.
Right. Safety first.
Exactly.
But assuming we can overcome those hurdles,
Mhm.
what's the timeline looking like? I mean, when could we realistically see this being used to clean up PFAS?
Yeah, that's the big question. It is the big question. It's tough to say for sure. But the research is really promising. And with the right funding, the right development, I think it's realistic that we could be seeing this technology being used within the next, say, decade.
Wow.
So imagine that, a future where PFAS contamination, it's just a problem that we can actually solve.
Now, that is a future I am very much looking forward to, I gotta say.
Me too.
It feels like we're finally, shifting gears from just managing PFAS to actually, getting rid of them.
Yeah, absolutely. And who knows what else is out there,
Right.
This research, it's just opened a door, and it'll be really interesting to see what other solutions we might come up with in the next few years.
Well, I'm feeling optimistic, I gotta say.
Yeah.
It's nice to be reminded that even the toughest problems,
Mm-hmm.
we can tackle them with a little bit of ingenuity, a little elbow grease, a lot of hard work.
I completely agree. And, who knows, maybe one day we'll look back and think, why did we ever call them forever chemicals?
Right.
It's true.
Hopefully one day. Well, that's all the time we have for today's deep dive into PFAS destruction.
It was fun.
Yeah, it was fascinating. We'll be keeping a close eye on all of this as it develops. But until next time, keep asking those questions and stay curious.
Absolutely.
See you next time.
See you later.